Bismillahirrahmanirrahim. This video is from Mr. Sedra's book on EDC, and here we'll be discussing example 5.1 solved in the book, and this is on the request of a student from Bangladesh. So let's just recall the structure of MOSFET transistor. This is the base or the substrate, it is called. The black ones are the metals, and there is a filling of silicon dioxide here. So, and the thickness of this is called TOX. So this we'll be using in solving the problems. This may look strange to you, but if you just do a simple technique, it will become familiar. And the technique is that you just turn it 90 degrees left, and you start comparing with the transistor. So this is the gate, is the base, emitter is the source, and the drain is the collector. And so now this should look familiar to you. And if you read the theory, there will be a channel here when we apply gate voltages. There will be path created and the electrons will flow through this. One more thing, we'll be using this width over length. So width is the width of the substrate, this W, and this main part, the metal part of the gate, its length is called L. So we'll be using these two also. Now let's come to the question. Consider a process technology for which the dimensions are given, and we have to find these three parts, part A, B, and C. So we'll deal them one at a time. First of all, the first part, TOX and K-N. While we are solving, I'll also try to discuss some of the theory part of it. So let's see. The COX is basically the oxide capacitance, or the capacitance due to the silicon dioxide. And the formula for this is the permittivity of the silicon dioxide divided by the oxide thickness. And so we can write it like COX is EOX, the permittivity of the silicon dioxide and the thickness of the oxide layer. And permittivity of silicon dioxide is further given by 3.9 e raised to the power O. E subscript O. This is the permittivity of free space, which is 8.854 into 10 raised to the power 12. So solving this will be EOX that we'll be using. Now F over M, F is for farad and M is for meter or per meter. One more thing, the formula now here is EOX, from where we saw F over M, and the thickness is in meters. So we have to keep this in mind. Now there is an important point, that generally the capacitance is represented in per micron squared. So what do we do? Let's see. From here we got the unit F over M square, but we have to convert this into per micron. So we'll use a technique of dimensional analysis. I hope you have learned in your classes. We want to eliminate M, rather M square, so we write M here and outside is the squared, and M is actually equal to 10 raised to the power 6 micro M, or the meter, 1 meter is equal to 10 raised to the power 6 micrometer. So now M square will get cancelled, and the value that we will get is we were here that to convert farad over m square into micron. We have to use the dimensional analysis, and here we have replaced this m and divided by 10 raised to the power 6 micrometer. So m square cancelled. So we'll have f 10 raised to the power 12 micrometer square. We'll go further. We take this up, so it will be 10 raised to the power minus 12 farad divided by micrometer square. There is still to go, and that is we will make it 10 raised to the power minus 15 by multiplying it by 1000. So multiplying here by 1000 and multiplying this by 10 raised to the power minus 3, so it will be balanced. And why we are getting 10 raised to the power minus 15? Because this has a very interesting name that we will use, and that is called femtofarad. So this is femto, 10 raised to the power 15 farad. Okay, so keep in mind that to convert farad over m square, we have to use 1000 femtofarad divided by micrometer square. So we'll use this in the problem that we are going to solve. Okay, so coming to the question, we had already discussed that it is COX is EOX over TOX. EOX 3.45 into 10 raised to the power minus 11, and TOX is given in the question, that is the thickness is 8 into 10 raised to the power minus 9. Solving this, we get it 4.32 10 raised to the power minus 3 farad per meter square. And as we discussed that we have to convert into micrometer, so we'll use this formula now to convert into micrometer square. So we multiply this by 1000, so 1000 and 10 raised to the power minus 3 will cancel. So 4.3 femtofarad divided by micrometer square is the answer. So this is for the first part of A. Now the second part of A is Kn dash. Now Kn dash is actually known as the process transconductance parameter, Kn dash, and it is given by this formula. Kn dash is mu n COX, where mu n is the electron mobility. Now if you recall, we had calculated COX already, and what is the transconductance? Just to give you an idea, just like the impedance is voltage over current, the transconductance is the current over voltage, but this is also admittance. But here the difference is that the current is output current and the voltage is input current, and therefore the parameter is known as transconductance. Okay, this is given in the question, mu n, the electron mobility. So we'll use these two terms here. So putting this, now there's a dilemma. This one is micrometer square and the unit here is in the centimeter square. So again we have to use the dimensional analysis technique to bring this also into micrometer, and the technique here is that centimeter will cancel it, so we bring it here centimeter, and we want to replace it with meter first of all. 1 meter is equal to 100 centimeter. Centimeter will get cancelled. Now there's a meter, we need to eliminate meter and we have to bring in micrometer. So we 1 meter down, and 1 meter is equal to 10 raised to the power 6 micrometer, and then we put square for this term. Remaining terms remain as it is, and so solving centimeter gets cancelled, meter gets cancelled, 10 or the 100 and they divided 10 raised to the power 6 divided by 100 will be 10 raised to the power 4. So 10 raised to the power 4 micrometer square divided by voltage per second, voltage and second, and this remains as it is. And now let's open this. 10 raised to the power 8 micrometer square per voltage second. Now micrometer square at the top, micrometer square at the bottom will get cancelled, so we get this term. And the dimensions of Kn are amperes per volt square, A over V square. Now this is not A over V square, so we have to convert this to get A over V square, and we'll use the technique of the relation between current. I current or the capacitor current is dq over dt is equal to C dV dt. So from here we can write that C over dt is IT over dV. And if we now note down the units, capacitance is farad, time second, current is ampere, and voltage is volt. That means V over S can be replaced by ampere over voltage. So let's rewrite this. From here we can write it as V over S into 1 over V, and V over S we replace by AV. So AV, and now this will be AV square. So 194 micro and AV square. So this is in the right form. So part A is done. Now let's go to the part B. For the MOSFET with WL 8 micrometer over 0.8 micrometer, we have to calculate these three parameters: VOV, VGS, and VD minimum. So we'll discuss what are these. To operate the transistor in the saturation region with EDC is 100 microampere. So first of all, this is the circuit that we are talking, and just for comparison I have done it here again. So this is the base and the emitter. This voltage is VBE is now VGS here. CB is VDG, and this is VCE is VDS. And then we'll take also discuss this characteristics diagram. And if you see, just from here, if you know that we need a minimum voltage of 0.7 for this transistor to conduct. Similarly, there is a minimum threshold voltage that we got to have at this point for the MOSFET to conduct, and this minimum voltage is called the threshold voltage. So in this diagram we are assuming that the threshold voltage is 2 volt. So this line is almost 2 volt here, and then we increase the gate voltage to 3 volt, then 4 volt, 5 volt, 6 volt, 7 volt, and 8 volt. Now see the shape of the graph. It is following the same pattern, but we'll discuss what is saturation. The saturation is the point, like if you take this big graph, the current is increasing, then at this point there is hardly any increase in the current. So this point we'll call the saturation point. Similarly for all these. Now this is the locus of the VD saturation. So here it is saturating, at this point it is saturating, and for let's say this graph, which is a VGS 8 volt, if we draw a vertical line, this is cutting at 6 volt. So 6 volt is the VD saturation for VGS 8. And how do we relate 6 volt with the formula? We'll use this, that VD saturation is equal to Vg minus Vt. So Vd saturation 6 volt is equal to Vgt, that is 8, minus V threshold 2, so it will be 6 volt. So this formula also we'll be using. Now let's come to the question. Okay, one more important point. VD saturation, this point here, is called override voltage or V override in Mr. Sedra's book. So this will be interchangeably used, that VD saturation or VOV. Okay, another important point, if you look at this graph, as we discussed, there are two portions. This is the saturation portion and this is non-saturation portion. It is called triad portion. So this is kind of a resistive area. Here we'll get the resistance relation to 1 I over V, Gm, and 1 over Gm will be R. So there are two formulas for current. One is for the saturation region and other is for the non-saturation region. So this is in the linear region. Now this is, we are calling linear region. This portion is almost linear. So in the linear region, we'll be using this formula, which is given by equation 5.7. And in the saturation region, we'll be using this formula, which has a half in it, and it is equation 5.1. I'll not go into the detailed explanation. It has been given in your book. And if you want to have a peace of mind, don't dig in, just assume that these are the two values. Okay. Question again here, we have to, for this, we have to find VOV, VGS, VD minimum. And since the transistor is in the saturation region, ID 100 microampere, therefore we'll use equation 5.17, which has a half in it. Now plugging in the values, 100 microampere, 1 over 2, Kn we just calculated 194 microampere per volt square, and this is the dimension given, and V square OV. Simplifying, microampere, both sides cancel, and then VOV can be calculated to be 0.32 volt. So this is first part of the question. Now VGS, VOV you have calculated, VT is given. So we'll use the formula that we have learned, that VD saturation, which is actually VOV, is VG minus VT. So this is VOV is VGS minus VT. VOV we know and VT we know, so VG we can find from here, VGS. VGS is 1.02 volts. So this is this voltage here, VGS. And the question is now the VDS minimum, that is this voltage minimum at the saturation. So this is the point where saturation is occurring. Therefore this is the VD saturation point, or also this is the VD minimum point or VDS minimum point for saturation. So we can write, to operate in the saturation region, VDS minimum should be equal to V over volt, which is 0.32 volt. So part B is done. Now we come to part C part. For the device in B, find value of VOV and VGS required to cause the device to operate as a 100 ohm resistor for a very small VDS. So two things, one is the we have to find the resistance, so we know this is the resistive region, and the second thing it says that for very small VDS, so VDS when we are reducing the small VDS, that means we are in the triode region. We conclude by noting that with VDS kept small, the MOSFET behaves as a linear resistance whose value is controlled by the gate voltage VGS. So this is the linear part. And we had already discussed that in the linear part, this is the current equation 5.7 we'll use. From here, if we divide it by VDS, this is what is remaining. ID over VDS is transconductance, GDS, and this is equation 5.9 that we are getting. Now GDS and RDS, 1 over RDS is 1 over GDS, and so it is 1 over this value, and mu and COX is also called Kn dash. We have seen this. So we were here. Now we'll plug in the value of Kn dash we had calculated earlier. We'll plug in the value of W over L, which is 10, and we'll also plug in the value of the resistance desired is 100 ohm. So from here we'll find the new VOV. So in this case the VOV will be 0.52 volt. So this is the first part, and for GS again we'll use the same formula that we have learned earlier, that VGS is VT plus VOV. VT is 0.7, VOV 0.52, so VGS is 1.22 volt. So this is how you have to follow and solve this question. I hope this gives you some idea as to the characteristics and various parameters of MOSFET. Please let me know through your comments. Thank you.